Yeah, my name is Joe Boardman, and I consider I'm a geophysicist, but mainly I work with imaging spectroscopy or hyperspectral data. But yeah, so I realized the other day with horror that I looked at my first airborne spectra in 1984, which is 39 years ago, which is scary. But then I really got into it for real when I started a PhD program at the University of Colorado from 87 to 91. And 87 to 91, my advisor was a fellow named Alex Getz. So he and Greg Vane really started the imaging spectrometer program at JPL. So they kept working on these airborne systems at JPL, in particular Avarice Classic. And that's where I kind of grew up in my imaging spectroscopy history. And Avarice Classic. And it was those kind of exquisite but bespoke instruments that I worked on for decades. And at the same time, some friends of mine, some colleagues, and I decided, hey, there's no software for this. So we created a little company and wrote a software package called Envy, which is now the thing I call Envy is now called Envy Classic. I have no idea what the new Envy is, but Envy Classic we wrote back in 94, and Envy just took off. And suddenly we became like a third of their gross and all of their growth. And Envy is a lot of places. I'm really proud of the work we did with Envy. So I've had this long history in this stuff and working on the R&D and the applications, but also back towards the instrument people, because my understanding of it as a geophysicist is we got to track how it's actually being measured, look at any artifacts that are in there and understand how they show up in the data and then how they affect the end use of the data. And oh my God, that became a horrible job starting in the late 90s and into the 2000s, because everybody and their dog somehow got a hold of a grating and a detector and call me up and they go, hey, what kind of lens should we put in front of this? We're going to really make some good, cheap imaging spectrometers. And I'm like pulling my hair out going, no, please don't. And they did it anyway. And there were some really crappy ones. There still are some really crappy imaging spectrometers. And what I want you to understand is the way I think about these things is like Landsat or an RGB camera or any of these things that we might call hypospectral, not enough bands. They're kind of like a hammer or a shovel, okay, that'll work. But an imaging spectrometer to me has to be exquisitely good and meet these certain thresholds or these hurdles before it's a detriment, right? Before you, like a bad imaging spectrometer is worse than none at all. Much worse, because I saw people lose their jobs by spending 800 grand on something that made crappy data that could not be repaired. And it really got to me. So then when I discovered that the HySpecs instruments meet the hurdles that I have for an exquisite imaging spectrometer, and at a price point that's down here where you don't have to be a NASA investigator, you can buy as many as you want, all these differences there, it made me feel better. So the reason I'm doing this and trying to explain to you guys about how important it is what you're doing to keep alive this business that I've been trying to help create for 40 years. And there was a time in there it almost got extinguished by crappy instruments. And I'm so happy that yours aren't crappy. So now we're going to own 8 of them soon. And we're really excited about it. And so we came up with this idea of these 4 hurdles. And also I got some of this from a colleague, Rob Green. And the idea is first that you have to have uniformity in the data. It has to be that every spectrum in the whole data cube has to be as though it was measured by the same spectrometer. You can't have 1,000 different spectrometers because you have non-uniformity across track. And then you have to have stability. You have to have the instrument be the same instrument every day if you're going to go repeat measurements, obviously. And then you have to have calibration, because we got to tie these back to national and international standards and the actual irradiance from the sun to convert to reflectance. So you have to have calibration, and then finally signal to noise. And none of this is any good unless your noise floor is low enough to tell apart the things you're trying to see. And these new instruments just weren't that great, to put it politely. They failed on those 4 hurdles over and over. And I saw this through a lot of manufacturers, and it really had me worried because the whole industry was getting now damaged in some way by bad instruments creating bad data, which I think are essentially useless, like a dull scalpel, right? If you can't make the data very good, don't bother. And happily, I ran across Trond in Brno, and he was giving a demo of a UAV system of all things. I sat in the front row and I was like, oh, here's another one of those horrible push broom sensors that's going to ruin my life. And he did the demo and he flew the thing and showed us the data. And he sent me some of the radiance data afterwards. And I started looking at them, saying, well, which hurdle are they going to fall on? You know, is it uniformity? Is it stability? Is it calibration? Or is it signal to noise? Boom, 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 boom. They made it over all 4. And that got us interested. And the company I'm working with now, we now own 8 of their systems, which I never thought I'd work for a company owning 8 imaging spectrometers. I mean, we may very well buy more, because not only have they hit those hurdles, they've done it at a price point that makes me happy, because I've been in this business for 40 years almost. And it's a very narrow world of imaging spectroscopy or hyperspectral data, and it's at risk of dying out, maybe besides some of the national programs you can't talk about. But to see a price point here where people who had, you know, basically dropped by a factor of 10 from some of the bespoke instruments that you really don't have access to anyway. So to me, there's these 4, you've got to go in order. Your instruments are unique in meeting these hurdles, and it makes me so happy. And that's why I'm here today to tell you, because I feared that these low-cost push broom sensors that were flooding the market, my market that I helped create, were going to ruin it. And so the idea that there is a choice, you guys, you are the choice. That's why we're buying so many of your instruments for ASO, Airborne Snow Observatory, where I'm now the chief research officer or some weird title. So we keep track of the uniformity, the stability, the calibration, and the signal to noise. And we've had instruments now for 2 years, I guess. It seems longer. Yep. But we've not seen a problem, which is very good. So thank you. All right. So I thought I'd show you some of what we're doing. God, I hate envy. So we'll go out and fly in a King Air, a Beechcraft King Air at, say, 24,000 feet. And that's as high as we can go with the LiDAR for the LiDAR to still work. So we're running a really nice Regal LiDAR 1562S. And at the same time, running the high specs spectrometers. And you can see in this zoom image here, or scroll image, that this is a mosaic of 27 flight lines over a period of like 4 hours of flying. And I just wanted to show you that, and then we'll talk about kind of the data content and how meeting those 4 hurdles makes possible some of the ways I think about the data. And the first thing, which never gets any love in imaging spectroscopy, is the spatial nature, right? So if you look in this mosaic, you can't see any seams, which is what we need, because we can't even be 1 pixel off, because we need the LiDAR and the imaging spectroscopy to be spot on at 3 meter pixels from 24,000 feet, which is hard. And with that camera model we got from your collimator, and us solving for roll pitch and yaw biases of that model, we get a perfect fit to the data when draped over the real topography. Because we're also flying the LiDAR, we get that day's topography, which is very nice for the ray tracing. But the main thing, I just want to point out how good your camera models are and how useful they are to us, right? Because you can see these seams radiometrically, but you don't see them spatially, right? That radiometrics difference is real. That's the phase function of the Earth, looking at it from different angles. But the fact that the roads don't go like this, bingo, there's 100 points for high specs right out the door. Here, reload. There. So now all the snow's yellow. Okay, well, that's bad. But anyway, the didn't mean to do that. Norway, no doubt you've seen it. So we're getting started here, but then people go, okay, why do you have so many bloody bands? Because if you look at a scatter plot, like we look at a scatter plot of two adjacent bands, say we look at band 10 and band 11, what do you think the scatter plot's going to look like? They have a correlation coefficient of like 0.99, right? And you show that to people and they go, oh, that's so stupid. Why are you measuring so many bands that are highly correlated? And we fought this for years in the early days. And the notion was that people would say, look, I can explain 95% of the variance if I just resample it to Landsat bands. We're trying to say, you're thinking shovel and hammer. We're thinking scalpel and some kind of exquisite instrument. It is that last 5% we care about, right? We don't want to use a multi-million-dollar instrument, but yours aren't. An expensive instrument to say, oh, here's the city, here's the forest. We want to go in and say, here's the yew trees, here's the spruce trees, right? Something you can't do with the other instrument. And it is this little difference that matters. But what we have is some abilities to then take all that information that's spread across all those bands and shove them up into a small number of principal component bands. And in particular, we like a thing I stuck into Envy called the minimum noise fraction. And the minimum noise fraction goes in, first we estimate the noise in the data. We estimate that, whiten the noise in the data, and then do a principal component shoving all the data up front. And so from here on, I'm going to show you, like this image is 18,000 pixels across, right? At 3 meter scale. So, we're down at the individual tree level, and I can't really show you, like it's a half a terabyte of data. So I can't show you processing on that because that's all done up in the cloud on little chunks. So I'm going to switch now and go to a resampled version of it. So all we've done is take every fifth sample of every fifth line. So we've only have 1/25 of the data here so that I could do this interactively. But this is after that transform, right? And the point about the transform is, well, if we do a scatter plot, now if we do a scatter plot of the MNF data, let's do a 2D scatter plot of MNF1 versus MNF2. So the way I think about the data is almost strictly in scatter plots and geometrically. And that's what I was getting at before, that we taught everybody for years to think, oh, it's a stack of images and a bundle of spectra. Yes, but what it really is, to me, after decades of messing with this, is it's a cloud of points in n-dimensional spectral space, okay? Where the location of the point in that cloud is the shape of the spectrum. So you can think of it as this third way of seeing it, not images, not spectra, but one n-dimensional cloud. And the location of every point in here is its spectrum. But the problem is, and here we get into a fun thing, these turn out to be some of the most complex data in the world. We'll look at the eigenvalues and eigenimages of this here in a second, but we'll often see dimensionalities almost always double digits and sometimes like 30 dimensions of signal just in the SWIR spectrometer. Because 30 dimensional, it's combinatoric, right? When in the US we have a regular lotto where you pick 5 numbers, and then they add this thing called the Powerball where you have to pick one more number is all. So it only sounds a little harder. It's sort of infinitely harder, right? Because it's combinatoric with the dimensionality. And the reason I'm so weird is because I've spent a lot of time thinking about these high dimensional scatter plots. But the good result is, and the fact that your instrument made these hurdles, right? Remember the hurdles. I've done this with, the reason I got so angry about the crappy instruments that were flooding the market, you can't do this. You can't make one coherent in-dimensional scatter plot if you don't have uniformity, stability, calibration, and signal to noise. And so all the work I had worked on all these years suddenly was just turning into vertical stripes because of non-uniformity and all of this crap. But with your instruments, it does not. And I want to show you something cool here. We'll go through an animation of the transform data. So you can think of this, basically it's a rotation. And it's an affine transformation. So there's a little shear in it, but and scaling, but it's mainly a rotation of your data. So instead of looking at it edge on, where we're looking at band I versus band J, we can turn our heads around here and look back down it, for instance, is one way to think about it, and see all these arms of these different things sticking off. And as you're seeing here, we're stepping through the first 25 of these MNF bands. So we'll start with 1, 2, it's by definition decorrelated, right? 3, 4, 5, 6, 7, 8. I mean, it keeps going, right? We have not run out of signal yet. We get out here, we start to run out of signal. And if I had built you a file properly with 181 MNF bands, which you have after you rotate the 181 that come in, you would see that out here at the end and everywhere beyond, it's all static. It's only noise. And this gets to a thing that this mathematician, Maurice Craig, I sat next to in Sydney during my postdoc, 91 and 92. I was coming from the US and the whole NASA world, and we called it imaging spectroscopy. And at the same time, that was about where the people we like to call the short-haired guys from Virginia, right? The intel and military folks, they were getting into this and they wanted a different name for it. So they came up with hyperspectral. Well, I sat down next to Morris and said, oh, isn't hyperspectral so stupid? That's such a dumb name. You know, why are they renaming imaging spectroscopy? I said, like, in the face of it, you're trying to tell your boss or your funding source, I want to build an instrument that has too many bands, hyperspectral. And Morris, in his own special Australian way, all he did was look at me and go, Joe, have you considered the alternative? And, you know, this old Okie had to scratch his head for a minute. I went, oh, you mean the other systems have too few bands? And so, you know, hypospectral, not enough bands. And what we're seeing here, and what has eventually kind of crystallized in my head at least, is that there's this upwelling radiance field, whether we're measuring it or not. And if the area is complex, that'll have real high dimensionality. Now, you fly over it and measure it. And it's, to me, I use this weird terminology. It's like, it's a beast. You know, there's this beast we're trying to capture. And if we fly over a 20-dimensional beast, because it's a complex scene with lots of things we can tell apart, if we fly over it with a 10-channel scanner, what's going to happen when you do the MNF? You're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you still have signal. You didn't have enough bands. It's hypospectral. But if you fly over a 20-dimensional beast with a 300-channel scanner, hot damn, we just captured the actual 20-dimensional beast in this 300-dimensional cage, if you will, right? That it was more than enough. It was capable of capturing the true shape of the scatter plot, not a shadow of it. Because if you don't have enough bands, well, all these scatter plots we show are shadows. Like here, it's a 2-dimensional shadow of, say, a 20-dimensional object. And we're going to get into this more briefly, but this whole idea of hypo versus hyper, I hope rings true to you and you understand the importance of these instruments and the fallacy of that argument about, oh, the bands are so highly correlated, right? It's like a cricket match, you know, it's 4 days long, but there's still something exciting happening. And you can jam all that up into like a 20-minute highlights reel, which is what the MNF are doing. But if you don't end up with an image like this at the end of your MNF, you were hypospectral, and you cannot do what I'm about to show you because you've only captured a shadow of your beast, not the upwelling radiance field itself. Okay, so we started looking at these two-dimensional scatter plots. You can think of a ternary diagram, right? That if you have material A, B, and C, you've got there at each corner, and then we have the thing called barycentric coordinates, but the mixing space allowed by three components has to sit inside a triangle. And do you know why that is? It's funny because it's very hard for people to get that, but the reason is so fundamental, and it was so weird in the 90s that the expert target detection people, they didn't understand the mixed pixel. They always called it the mixed pixel problem. And I turn it around the other way and say, no, it's our spectral leverage because we have mixed pixels. We're not listening to radio signals, listening for a target signal in the radio signal. Because in a radio signal, if you hear this noisy background and then someone injects the target signal into it and you're supposed to alarm, it got louder, basically. You had the original signal plus the new signal of the target. We can't do that with our pixels, right? Because our pixels, whatever they have in them has to be non-negative in abundance. There's no such thing as negative kaolinite. And they have to add to 1. It seems so stupid, but we call those the feasibility constraints. And the feasibility constraints of the fact that we are limited to mixed pixels, we turn it around from being a problem to the total leverage we use to do what we're going to show next, right? That you can say, just like in that chemistry diagram, the purest pixels are out on the corners because of the feasibility constraints. Because you can't go past 100%, because that would require negative abundance of something else to stay in the same plane. And so the problem here is, it's great to understand these as mixing simplices due to the feasibility constraints, but when you get to 30 dimensions, it's like game over for the closed form solutions because of numerical accuracy and just the unimaginable vastness of a 30-dimensional space. There's no way to get the right answer, right? You don't win lotto very often. So we got some ideas, and we're going to use this fact that we have mixed pixels instead of a problem. We'll use it as leverage, right? Because if you just look at this scatter plot alone, you say, look at that arm sticking out there. I wonder what that is. You say, okay, well, it's something up here in the image. So the 2D scatter plot, wherever it went. All right, so you see this point out here, and we can put a Z profile on this, but from the radiance data where the spectral will make sense, right? So we have a radiance cube and the MNF cube that line up, of course, pixel for pixel. So the point is, you start to look at these scatter plots, and you think, oh God, how could I ever look at all combinations of every 2 set, even if we've reduced it down to say 20 dimensions? And you can't, right? But you get the idea that if you scatter plotted, say 4 versus 5, you're going to get an equally informative, but very different, here's something sticking out here. And it looks like the snow they're building on the ski runs, in fact, right? And you realize, wait a minute, it's fine to understand this as a scatter plot in high dimensions because you've met the 4 hurdles, but there's no way in hell you'll be able to sit here and kind of manually parse this out. Because what we want to do is find those pixels that explain all the others as mixtures of them. Right, so we'll go back here to a more interesting one. Actually, we'll go back to 1 versus 2 because I want to show you that in the other. So there's a scatter plot of all the pixels in this particular image, and you're thinking, well, I start to see some of these arms, and it turns out in very high dimensional space, right, in like 20-dimensional space, which this scene needed, as we've shown with the MNFs and the eigenvalues, you start thinking, well, how do I fill in that 20-cornered simplex, and how many pixels would I need to actually occupy meaningful density in there? There's not enough pixels in the world to do that. Never have been. So the point is, even though it's 20-dimensional as a big rectangle, no individual pixel probably has all 21 materials in it. And so what this scatter plot is really made up of is this web of interconnected mixtures that do exist. And it only looks solid like this when we project it down to 2D to sit on our screen. And so only certain mixtures exist. Some pure pixels exist, some don't. And it's a very complicated beast, but I think of it more than a blob. It's like a web. It's like a spider web of possible mixtures that do exist and how they lump together because of the rectangle you've chosen to say, this is my scene. And here it's this 4-hour flight because you've got such good stability. So we came up with the next thing. I actually invented this part called the pixel purity index. And the idea is we'll never be able to do closed form computational geometry in 20 dimensions. So we turn around and say, okay, I want to find the purest pixels of any flavor. So find all the pixels that are out on these pointy arms that stick out like a sea urchin in 20 dimensions. And so what we do is we take the thing and you think of it like a rock tumbler, or you're rolling it around on an ink pad in 20 dimensions, and you're counting how many times each pixel gets hit. And that's the thing we stuck in NV and called the pixel purity index. I won't run it here, but I have a pixel purity result. And the pixel purity result looks like this. There we go. And after you run the pixel purity index, you get out a grayscale image and you think, well, that doesn't look very interesting, but we have to re-stretch it here. All this is a count of how many times each pixel was found to be external. Because if you're external in a projection, you have to be external in the full space, but not the other way around, right? External things can get hidden in a shadow, but external things that are in the shadow must be external on the edge of the data cloud in the real full space. And so if we say, well, just show me the pixels that got hit more than 50 times, suddenly we end up with focusing our attention on less than 1% of the data, okay? And we'll go in and say, we're gonna do, make a region of interest and say, okay, I wanna get a region of interest from only the pixels that were, say, above 50. And now we're going to do something fun. We'll go into the ND visualizer where we're not going to be stuck looking at two-dimensional data anymore. We're going to be able to see it as an n-dimensional. So you can see now this scatter plot has the very same shape that our other one that we were looking at, but we've hollowed it out, right? Okay. Right? This has the very same shape as this one, as the colored one. But the color one's got 1 million pixels in it. This one has 90,000 or something, or, you know, we're down a factor of almost 100 in terms of the number of pixels we need to understand, but we can understand all the rest of them as mixtures of these. And the cool part is, right, you can turn on any set here and start to see these different arms of the different signatures in the data sticking out. Why is it doing that? But you can also, this is the fun part, if you haven't done this ever in NV, you can start it rotating, right? And once you start it rotating, you suddenly realize how inadequate a static 2D shadow of a 20-dimensional object is, right? And right now, here, I'll turn on some axes just to confuse you, but there's the axes of the first 3 MNF bands, right? So it's just looking at a 3D rotation of those, restricting our attention to only the purest pixels of the whole scene without trying to separate trees from snow and the 9 different flavors of snow we can map. But the trick is 3's just as bad as 2, really, right? And so we'll turn on 2 more dimensions here. And it starts to do some things that don't look like rotations, and I can turn off those axes and slow it down. It'll start to do these things that don't feel like rotations because it'll pick up and fold through itself. But that's because we don't understand what 5 space is like. It doesn't look like a rotation to us, but it is a rotation. And what we're doing is just picking random projections of it into this space we've lit up, pick another one, and then follow what they call a geodesic, which is the minimum spin path between those two. And it starts to give you an idea about the data. So we could say, let's put a profile on here and say, well, what are these things that stick out? And this is what I was trying to do before. So now I have this spectral profile, and I can come down here and say, well, what is this stuff? Oh, that's snow. I recognize the snow spectrum here. Or because it's calibrated, we can bring in reference spectra here and say, oh, that is the snow arm that sticks out. And you say, well, how about what's this over here? And I'm down here in the bottom corner and moving around, and you can collect spectra and say, oh, of course, those are all very similar because they're in the same place in the n-dimensional cloud sticking out on a corner. And then we've got maybe a guy over here. What's that? And that's different. And what we're looking at here is different kinds of snow. And your instrument's so beautiful that we can go down here and say, okay, well, there's this kind of snow, and there's this kind of snow. And if we start it rotating, do those hang together, or have I painted something that doesn't belong because of the projection? And you can see that, I didn't, because those were such good ones. But you say, what's this stuff over here? Well, that's vegetation. This is like the vegetation arm sticking out, right? I just know these from the spectra, but you could compare them to a library. This is the shade corner, oddly enough, right? That there's a virtual end member called shade where everything retreats to as you turn down the light. And we're able to go in here, say all of this is snow. That there's a completely different snow yet, right? So I'll pull up, and I'm pulling up those three right now, and you can see the kind of different snows we're getting out. This one that has this huge, strong feature right here, that's very wet snow, that's isothermal and is full of water. And so you're getting that beautiful water feature right there, and absolutely no reflectance out here in the sphere, which oddly enough, we use as a signal, right? Because that's its shape, so it has a unique position, even if it's zero. And then these are other snows that are drier and colder. And so we ended up finding like 5 flavors of snow here. And you can start to do fun things like we can collapse these. So now we've turned this red to warn you, you're no longer in MNF space, but you're in a transform of MNF space, so be careful. But what you'll see is what I did there was I collapsed the red, the green, and the blue classes onto each other. And because there's 3 classes, well, they span a plane, so that's 2 dimensions. So let's take 2 dimensions and take them out of the mix so that you can never see the difference between the red, the green, and the blue anymore as long as you're in the collapse space. So we can make all snow, all these different snows look like one snow, and they map them against the varied background with a mixture tune match filter, which we don't have time to talk about, but it again leverages that feasibility constraints where a regular match filter is more tuned to like a radio signal target detection, not pixel stuff. And it's only because you guys met these 4 hurdles that we're able to do this. We tried this with, name them all. They're not good enough to do this, but your instruments are. So I basically wanted to show you some of this and say thank you. I don't know how you do it, frankly. It's interesting because like when you movie through the MNF bands, stripes are a signal, right? That this should find if they're there. So a lot of the bad instruments, you'll get MNF1 is the illumination, whoopee. We already knew the topography. MNF2 suddenly starts showing vertical stripes because they don't have uniformity of the detector and the responsivity. And then this game over, right? Like it's a dull scalpel and you can't use it. It's not like you can fix it by normalizing it all and all these things. So mainly the answer is they show up either in vertical stripes or horizontal stripes with these 2D systems if there's a time variation or if there's a responsivity that's changed since the calibration, or maybe they didn't do a good calibration in the first place. And that's like, so your scatter plot ends up with all these disjoint parts as though it was measured by 27 different instruments, one for each flight line. Plus you have all those stripes that you sure as heck don't want in your final snow map, but you can't get out because they're already embedded in the data. And so what we mainly do with the spectrometer, I mean, we don't use it to its full extent, right? Because there are many, you could do forestry with these, you could do aquatic studies, you could do all sorts of things, urban studies. But all we're trying to do is map the multiple different kinds of snow that are out there, collapse them to be all snow, find the background that's not snow, and then get a mixture, tune, match, filter abundance image of the snow to compare that to our depth images from the LiDAR before and after it snowed. And then we can say, let's believe the depth images where the spectrometer says there really is some snow. And that's easy above tree line. It's very hard to do in the forest because you can get these false depths out where we've got to use the unmixing of the snow in the presence of a tree canopy to go in and say, no, those are the depths we believe, and we want to integrate into the water model. And these other depths are spurious things like a bush has grown, or there a tree or rock rolled downhill, or whatever, right? So we use it in an integrated way with the LiDAR, but the main thing we're doing with it is just trying to collapse all snow into a target and map it against the background and say, where is there snow? And there's so many PhDs in our data that aren't getting written, right? Somebody could take this one data set and do all this beautiful snow physics about all the different flavors of snow and mapping them on the ground. But you know, we're trying to earn a nickel, so we don't have time to go do that.
No.
I hope that made sense.
For sure. Thank you very much, Joe.